explaining the OPAM usage or OPAM usage in practice in this video. Already we examined the operational amplifier, ideal operational amplifier definition relation, which is this. So we have done this. Now we are saying where we are going to use this operational amplifier in practice. There are 6 alternatives that we are going to give you here. There are many others, of course, but I will be introducing just 6 of them in here. And we are going to do the analysis for these circuits and find out what the function of these circuits, what these circuits does. By analyzing them, we are going to tell this what they do or not, what they do in practice. So these 6 examples like that, what are they? Inverting amplifier, non-inverting amplifier, summation circuit, difference amplifier, buffer, and independent current source. So by using the just one operational amplifier, we're going to we could introduce all these circuits which does a specific job. So let's start from this one, inverting amplifier. So what we have here, this is our operational amplifier, definition relation is given here, and plus terminal is connected to the ground, that means this voltage is 0, and the negative terminal of my operational amplifier is connected to a independent voltage source in serial Vs. You might consider this circuit here as a Thevenin equivalent circuit of a given circuit. So you might consider 2-stage cascade connected to networks or circuits connected together. Cascade connection means if circuit A output is connected to circuit B input, we call these 2 circuits are connected in cascade. So you might consider this is the first cascade circuit, represent the cascade circuit Thevenin equivalent of this circuit. As we already said that without any feedback element, operational amplifiers do not work, they burn, and there is a resistor on the feedback path from output to the input here. Now we're going to, it says that this circuit does inverting amplifier. Why inverting means make the output as minus, as you see here, minus, inverting. Non-inverting makes this sign plus. It is an amplifier, that means it amplifies the inputs and gives the output. So this might call the gain as well. So if RF is bigger than RS, so it's going to be bigger than 1. Since it is bigger than 1, it is an amplifier. It increases the input voltage to a higher output voltage. It is an amplifier. And the sign of this output voltage is going to be negative. Whatever the sign of your input is going to be multiplied with -1. That's why it is an inverting amplifier. So how are we going to make the decision whether this is an inverting amplifier or not? So we are in this circuit, this is not given to you. This circuit is given to us, and we are saying this is an inverting amplifier. What I could do is this, calculate that V0 and interpret the mathematical relation that I found for that V0. How I am going to calculate this V0? V0 is the output voltage, and output voltage, all the elements, current and voltages can be represented in terms of the independent variables. So V0 is going to be calculated in terms of V0. V0 or Vs, in terms of Vs I should have said, V0 over Vs is the output of my circuit. So how you're going to end up with this one, I am not going it step by step, but I can explain it how you end up with this result. Consider that node here and write the Kirchhoff current law equation for this node. What is this element current, RS, resistor current? This voltage minus this voltage. What is this voltage? So you see that plus terminal voltage is 0 since it is connected to ground, that is short circuit. So this voltage is 0, so therefore this terminal voltage with respect to ground is 0. Since Vp minus Vn, so voltage drop between those two terminals is equal to 0, that means that ground comes here. So that is 0 voltage here, almost 0 voltage here. That means ground. So then we can say that Vs minus 0 over Rs gives this current here. And since the definition of the ideal operation amplifier is this, that IN current is equal to 0, so that means we are writing Kirchhoff current law equation for this now. This current is 0, I didn't write that. I wrote this current as Vs over Rs. And let's come to this element current. That is the node voltage, one of the node voltage for RF, V0. Another node voltage is this, which is 0. I already explained this node voltage is equal to 0 because this is short circuit and this is connected directly to ground. So V0 over RF is the current of this. So this current is 0. Two currents you're going to add and equal to 0, Kirchhoff current law equation. From this equation you end up with that result. Let's interpret this result now. Output voltage, it says here, output voltage is independent of the load. What does this mean? Why it is independent from the load? So what we are saying here, whatever you connect here as a load RL here, it doesn't affect that gain here. Why is that? Because I wrote Kirchhoff current law equations for this node. I end up with this, and this doesn't depend on the RL value, and I could say that gain is independent from the load. What does this mean? For any load, if the voltage is the same, so that means it behaves as an independent voltage source, isn't it? So if you say that independent voltage source is the voltage is known, and whichever circuit you connect to that independent voltage source, this voltage source voltage does not change. That is independent voltage source. And this is also the same thing happening here. Therefore that V0 here or V output here behaves as an independent voltage source. That is the one interpretation of this mathematical relation. Vs and Rs could be considered as a Thevenin equivalent of a pre-circuit which is connected as cascade. Pre-circuit, I am talking about two circuits connected in cascade here, and this is going to be the pre-circuit, that means the first circuit in the cascade connection. And this first circuit, Thevenin equivalent, can be considered as those two elements connected in serial. And then look at the output now. Gain, it is an amplifier. Why it is amplifier? If RF is bigger than RS, so this is bigger than 1. Since it is bigger than 1, that means this is going to be an amplifier. What does this mean? Bigger than 1, output is bigger than the input. It is inverting, it says, because of the minus sign here it is inverting. RF and RS values always positive real numbers, so that's negative makes it the output negative. Whatever this sign you got for Vs is going to be the opposite sign at the output. How gain is controlled? This mathematical relation tells us some more information as well. How I can explain that? If your RF value, that is the feedback resistors, when you change it, your gain is going to change, isn't it? Consider that Rs is a constant and you are changing the RF, So that means you are controlling your amplifier's amplifying coefficient. Why we are not changing the RS value but could change the RF? As I said already, these two serially connected elements represent the whole circuit which is connected to here, and I cannot play with this circuit, but I can play with this feedback resistor here. By playing with that resistor, I am controlling the output voltage or the amplifying degree of my circuit. So we said here this is inverting amplifier. There is a non-inverting amplifier here. The difference, as you see here, these two voltage and the resistor in series connected to the negative terminal, but in here it is connected to the positive terminal, and there is a resistor in this internal negative terminal here. So if you do the analysis, I'm not going to do it step by step, but just to interpret the result here. So that's the definition relation of our ideal operation amplifier. I said I'm not going to explain it step by step, but I can tell you what the rule is. Try to write the Kirchhoff current law equations for this node, and then use this information anytime you need, because this is the definition relation. You can definitely use it anytime you like. If you do the calculation, you end up with that result. So let me focus on that. So you're going to end up with that result. That result tells me what? This denominator is bigger than denominator because RS plus RF and over RS. So that means this ratio is bigger than 1. So it is an amplifying, and this is the voltage gain. So you can increase the output voltage. Here, how I'm going to control it? By RF, of course. You cannot play with this RS value. Gain is controlled once again. So the difference between this one and this one here, non-inverting and inverting, is that sign. There is a minus sign here, but in here there is no minus sign. That's why it is non-inverting amplifier. So these are two applications of these operation amplifiers, usage in practice. Let's come to the other applications of these operation amplifiers. That is the summation circuit. Summation circuit, we've got 3 input voltages here, and this circuit output gives me the summation of these voltages. So if you write a Kirchhoff current law equations for this node, this is just one node. So if you're writing the Kirchhoff current law equations for this node, that means you're going to write 1, 2, 3, 4, 5 current terms here. Anytime you need, you could use the operation amplifier definition relation and then calculate the outputs in terms of the inputs VA, VB, VC. You end up with this. If you look at this, if you choose that RF, RA, RB, RC resistor voltages equal to each other, then this becomes 1, and this becomes 1s, and this becomes 1s. That means output is the summation of the input voltages and negative sign in front of it. So that means inverting. So that is the summation. You might consider this as a calculator. So let's say you have voltage values of VA, VB, VC. The output of this the output of my operation amplifier gives me the addition of these voltages. That means you have done the summation of the inputs. That means calculator, isn't it, which does the summation operation. This is at the same time, once upon a time, used as an analog computer. These operation amplifiers, first time they were used in analog computers. So they become historical equipment anymore because we've got the digital computers now. But there are some other facilities that we could use here. We could multiply any voltage that I have with any coefficient I like. So for example, if you got the RF value, choose RF value, any RF value you like, and you would like to have a coefficient in front of a VA. So you according to the coefficients that you have chosen for the VA volt is going to be determined by the RI value change. Example, RF 100, and you would like to put 2 in front of VA, you're going to choose the RA is 50. 100 over 50 gives you 2, so you made a coefficient 2 for VA. So you can, by changing the RA, by choosing the RA, RB and RC values, you can arrange the VA coefficient, VB coefficient and VC coefficient as you like. So you could do the summations for different coefficients of these voltages. So how you are going to control the output value? You could increase this output voltage by choosing the higher RF values. So this is the summation now. So once we have seen the summation, let's come to the subtraction or the difference amplifier. So it is this one. Okay. Here is the circuit, and once again the definition relation of our ideal operational amplifier is this. If you do the analysis of this circuit, so V0 is going to be equal to this. So you do it your hand. Once again, write the Kirchhoff current law equations for this node, so you're going to end up with this. So it says here, if this RF, RS, RA and RB value is chosen according to that equation, that means ratio between RF, RS is equal to ratio of RA over RB, then this becomes this. If we look at this now, VA minus VS is the difference between the available voltages, isn't it? So that means my output, if RF is equal to RS, my output is the difference between those two. So that is the difference amplifier. So if you choose that RF equal to RS, RF equal to RS, then this difference VS, VA over VS is going to be equal to V0. That means difference, isn't it? So it says amplifier, so you can amplify this difference by choosing RF and RS value. RS cannot be played with it, but by choosing the RF value, you can amplify your input difference to any value you like at the output. How you can control it? You can control the gain once again by changing the RF value. By changing the RF value, let me explain you a bit. When you are talking about the amplifiers, so you know you've got amplifiers while you are listening to music. You are using amplifiers. The volume knob in that amplifier is that RF resistor that you are playing. That means when you are playing with this volume knob, you are changing this gain. That is volume then. So we examine now four application of the operational amplifier in practice. Now let's come to the fifth one. It says buffer circuit here. I will explain what buffer circuit is as well. Let's do the calculations and then explain what the buffer is about. So once again we have a circuit here, and that's the definition relation of this operational amplifier as an ideal operational amplifier. Now we are saying this V0 is equal to Vs. You might say that if V0 equal to Vs means directly connect that to here, but it is not like that. We put that element inside. Now consider for a while, imagine that, remove all this operation amplifier and connect that RS resistor in serial to RF. So what's going to happen is this. You can consider this serial connected VS independent voltage source and RS as a Thevenin equivalent circuit of a given circuit. So this is going to be the load of my circuit. So I have replaced the Thevenin equivalent circuit with a given circuit and put an R value here. So that means RL is the load resistor. So the current passing through this resistor is going to be Vs over Rs plus RL. That's the current. Now keep in your mind this I value when there is no operational amplifier like that. When you put the operational amplifier in here, see what happens. So it says definition relation that IP current is equal to 0. That means this resistor current is 0. Then the voltage of this resistor is also 0. In this case, this plus terminal voltage is equal to Vs. Since Vp minus Vn is almost 0, that means there is no voltage drop here. So this terminal voltage is also Vs. So that means your output is equal to Vs. So in this case, RL load resistor voltage is going to be equal to Vs, the current Vs over RL. If you don't use this operational amplifier, the current was going to be Vs over RL plus Rs. So depending the Rs value, your current is going to change here. But what we are seeing here, this becomes independent from Rs. That means your V0 here or V output here behaves as an independent voltage source. There is no voltage drop here, so that's independent source seen here is directly transferred to the output of your operational amplifier by this circuit. So that means you are transferring this voltage source as an independent voltage source here. That's why it is called buffer. So if you don't use this buffer, now you could do this, for example, this test. Compare RL elements power when OPAM in and out. You're going to see that the power that you transfer to this load without the operational amplifier and with the operational amplifier is going to be different. The difference is going to be, if you use the operational amplifier, you transfer bigger power to your load. Without this operational amplifier, less power that you're going to send to the load. Less power, that means efficiency dropped. So efficiency, in terms of efficiency, it is very critical to use an operation like that as a buffer to increase the efficiency. And the last application that we're going to see, application of operational amplifier, the last one, is this independent current source. When we were talking about the independent sources at the beginning as the circuit elements, we said there are independent current sources and voltage sources, and we gave the example what is the independent voltage source. For DC source, we said accumulators and batteries that we use, these are all DC sources. And we also said that there is an AC independent voltage source as well. These are the power points or power plugs that we use in our houses. So available and very common in every house. And at that time we said there is an independent current source as well, DC or AC form, and this is not available in every house, we said, but electronically we could design a circuit behaves as an independent current source. That is the example to that. This independent current source is a electronic circuit like this by using an operational amplifier. Now let's calculate this current in the array resistor here. So we could say that we are going to use it in the ideal operational amplifier definition relation. So this is Vs. Since IP is equal to 0, that means the resistor current is 0, then the voltage is 0, so this is Vs. Since Vp minus Vn is equal to 0, that means voltage drop between two terminals is 0, so Vs voltage at that positive terminal becomes the same as the negative terminal voltage, that is Vs. So Vs came to here now. The current for the RA resistor is going to be Vs over RA, that's the current. So if we consider the Kirchhoff current law equations for this node, by the definition relation in here, I know the IN is equal to 0, that means this current is 0. Since this current is 0, the current of this resistor is also the current of RL resistor here. Means this IL current of this load is the same as the current of this resistor, which is Vs over RA. Result is this: IL current does not depend on the RL resistor. Means whichever resistor you connected to this element, whichever resistor you connect, so that is this part, represent this point dot dot circuit here, which is independent current source, of which current is this, and this current is independent from this load resistor. So definition of the independent current source was the current is known, and whichever circuit it is connected to it, that current do not change. Here you are, whatever the RL value, this independent current source current do not change, and this current is equal to Vs over RA. So we made an independent current source by using an operational amplifier circuit like this. So we just examined 6 of the usage of an operational amplifier in practice, and the next we will be examining alternative models for OPAM. In here, while we're explaining here, we said ideal operational amplifier and use a simple definition relation. Now we will be saying that there is an alternative to this, not that simple as this, but more realistic. When it is more realistic, what would be the difference we will be examining in the next video.